Then hello everyone to our very first international online seminar on interval methods in control after our summer break. It's my great pleasure that we can celebrate today the third birthday of our seminar. And yes, in fact, that's the 58th presentation that we'll have today in the series of our seminars. And it's my great pleasure to have you here, Yong. Yong received his Bachelor of Science degree in Germany, in fact, at the University of Applied Sciences in Esslingen. Afterwards, he did his master's studies at the MIT. And currently, he's an associate professor at the Mechanical and the Industrial Engineering Department at Northeastern University in Boston. And I think without any further ado, I'll hand over the floor to you, Yong, and to give you a presentation about robust control barrier functions for uncertain systems with set membership estimation and learning. The floor is yours.
Hi, thank you so much, Andreas, for the introduction. And also thank you for this honor to be giving this talk on the third birthday of, this seminar. So as Andreas mentioned, my name is Zheng Yong. I am currently at Northeastern. Some of this work that I'm presenting is based on some of my collaborations with my former students and current students, previously at Arizona State University, where I was at before I moved to Northeastern. And today I will be talking about some of my work or our work on robust control barrier functions for uncertain systems. Specifically, the tie-in with this seminar is how we can use some set membership estimation and learning techniques for combining them with control barrier functions. So let's move on to the next slide. So I guess I would just say that a lot of our research in my group, we kind of focus on safety critical cyber-physical systems. So as you all may know, there are a lot of different physical systems that have also a cyber component. And we want to make sure that these systems are safe. And we want specifically the context of a lot of the research that we do is on making sure that they are robustly safe, even when there are uncertainties in the system. So let me just introduce quickly set-based methods in control. That's something that perhaps is not foreign to a lot of the people in this audience, but in case this is not quite known, so basically sets generally or naturally appear in control systems design. Constraints are usually written as sets or can be viewed as set constraint. Uncertainties are when uncertainties are bounded, then we can consider them as sets as well. And design and safety specifications can also often be expressed using sets. And when we talk about sets, there are different types of sets that we can consider. So polytopes, zonotopes, hyperrectangle or intervals or ellipsoids. And I guess in the context of this, presentation or this seminar, we will be focusing quite a bit on the interval part of it, but I guess we are also using some of the other techniques for the other sets. So they are found in a lot of different types of problems. So I guess they are used for reachability-based verification and planning. They are also used for set-based control, set-valued estimation, and also set membership learning. So this talk would be based on, I would say mostly 2, 3, and 4. So we are combining all of them. To some extent, we are doing, we can view robust control barrier functions as a set-based control method, where we will apply some set value estimation and also set membership learning to deal with uncertainties. So again, this is just more of an introduction for control barrier functions. So control in general, when we deal with safety, we often talk about control invariant sets, meaning that we want to find a set of what we call a safe region. If we start within that set, then we want to make sure that we always stay with it. There always exists a control input such that we stay within the set. So, and that's desirable. Basically, that's just saying that if my system was safe, we want to make sure that we can always choose the right control. There always exists some control inputs that we can choose, and we have to choose them so that we remain safe, remain within the set. So this problem here can be quite difficult to compute I guess, because especially if the systems are nonlinear, they can be, or when the dynamical systems are nonlinear, they can be hard to compute, or the maximal set that's safe, it's usually hard to compute. So people start using what we call control barrier functions, where control barrier functions can be thought of as a special case of control invariant set, where we assume some things about the system. We essentially, it functions like a Lyapunov function, where it's, I guess, if we can find a control barrier function and we can enforce it, then we know for sure that that set would be control invariant also, but we don't quite care or guarantee that they are the biggest one that we can have. So in this setting here, generally people consider control affine systems that are known, and there's a safe set that's defined using a function h, and it's called a CBF if the final condition that holds, meaning that there always exists an input such that h dot essentially, or dh dt, is greater or equal to 0. So when it always stays positive, and at the boundary, we can think of it as the h dot has to be positive. And so because of that, it will always remain positive. And if we define h being positive, being safe, that means if we stay within that all the time, then we know that the system is safe. So this is often used as a safety filter in the literature for control barrier functions. Specifically, they would take the conditions, the final condition there that's written with Lie derivatives directly, in this case, as a constraint. And we use that to modify a nominal controller or a legacy controller that people might have. And we just solve this here. And this here would be actually generally a QP that can be solved. And this here would be a safety filter that would just use the inputs from the nominal controller if it's safe. But if it's not safe, then you can think about this as just kind of finding this closest solution to the nominal controller that keeps the system safe. So that is partially the reason why this is called a safety filter. Okay. So this is what generally has been considered. But what are the challenges that we are facing here? So first of all, systems are not always known. I guess they are uncertain. So there will be two parts to my talk today, and one would be on systems where there are actually parameters that are uncertain, meaning we don't really know them, and they could be time varying. And we will also consider systems that are uncertain in the sense that there is no mathematical model of them, that's no mathematical model that's available at all, but we have some data that we will use to learn what this model is. And so we are going to be assuming that we are given an uncertain safe set. And the question here is then, how can we guarantee that we will be safe, meaning that we still have control invariance for both types of systems where the systems have either uncertain time varying parameters or there is no mathematical model at all, but we have some data or some prior data of the system. So how do we go about doing this? So what we would be looking at right now is we will be looking at robust control barrier functions. Okay, so just to give an overview of the talk, I will start a little bit based of my talk, focus a little bit on what we call mixed monotonicity, which is a property of quite a general class of nonlinear functions that will actually enable us to do a lot of the things that we are doing. So basically, a lot of the methods that we would be talking about in B and C, which is the robust control barrier functions for both classes of systems, uncertain systems that I talked about, we'll be using things from mixed monotonicity. So I would first introduce that as well as present some work on, I guess, how do we use that to do to design interval observers, and how we can, before we go into actually the control barrier functions and how we apply them. Okay, so let me just start by defining that. If you are given a nonlinear function f, we say that it is discrete time mixed monotone. So basically this here is for discrete time systems for now. There is an extension for continuous time systems that is it's not very similar, so I'm not going to talk about it. But basically what it's saying is that a function, a nonlinear function, is discrete time mixed monotone if there exists a decomposition function, a function where we lift the dimension of the system from just the domain being just Rn to 2 times the dimension of the system. So it's a 2n dimensional system where it satisfies these 3 conditions. Number 1 is that this decomposition function, we call it being embedded on the diagonals, meaning that if both the arguments of the decomposition function are x's and they're identical, then it will recover the original function. So that's the first condition. The second condition basically is just saying that I guess if it will be increasing in the first argument and or non-decreasing in the first argument, and the third condition is just saying that it is non-increasing in the second argument. So basically we lift it up from just n-dimensional system or n-dimensional function to a 2n dimensional function, and I guess it satisfies these 3 properties. So why is this nice? It's really nice because if we start dealing with intervals, when we have x being within a lower underlying x and an upper line x, meaning this here is actually an interval, then we can also bound the output of this function as an interval, where it simply is given by this decomposition function with the order of the x upper bar and x lower bar being switched. Just based on the property, we can easily show this. So what this here allows us to do is actually enables us to do interval bounding of nonlinear functions, and that's what would really help us to deal with, I guess, all the design that we want to come up with. Actually, this is also very useful even for linear functions, but generally what it's really useful for is that it can do interval bounding. The only issue with this is that, well, we say that there exists a decomposition function, but we have to actually design the decomposition function. And it's been shown that decomposition functions are actually not at all unique. So that probably means that there are some decomposition functions that are useful, or their bounds are actually tighter, and they might be decomposition functions that are terrible and they still bound the function, but the bounds can be bad. So the trade-off there is we want to find bounds that are as tight as possible, but we also want to find bounds that are computable or easily computable, which we call tractable. So we say we want to ask the question, can we tractably find some decomposition functions that will be as tight as possible? Actually, it can be shown that the tightest decomposition function generally will involve some nonlinear optimization problem that will give us the decomposition functions, but they are generally difficult to solve. So this is just to give you a foretaste of kind of some of the work that we've done. We came up with what we call a remainder form decomposition function. I won't go into the details, but basically what we could show is that it is the tightest in the family that we consider, and that includes a specific version that was proposed recently in 2019. And we said that it is also tractable or computable. So basically, we don't need an optimization problem, or we don't need an iterative algorithm to solve it. We can solve it all in closed form. And it actually even applies to non-smooth or semi-continuous functions. That's what we've shown. So generally, I guess the easiest way to think about it is that if the function is Lipschitz continuous, then there always exists one. But we also showed that even when the function is non-smooth or semi-continuous only, we can still show that those functions can be mixed monotone. I guess can be mixed monotone. Basically, we can find the mixed monotone decomposition functions. So what we also find is that it's not always true, but if we use this specific way of bounding using this remainder from decomposition functions, it actually outperforms quite a few of the variations of natural inclusion in interval arithmetic, for those that are familiar with that. One other good property about these decomposition functions is that actually for a system, whether it's continuous time or discrete time, we can always find a pair of decomposition functions and write down what we call an embedding system. And the embedding system has a certain way of writing them. But once we write down the embedding system, we can actually solve that. If it's continuous time, we can just use ODE to solve it. Or if it's discrete time, we'll just propagate it in time. What we can show is that if we write down the embedding systems, then I guess we have automatically this framer property, which means that the true state of this continuous time or discrete time system will always be within x under bar t and x upper bar t that we compute as a solution to this embedding system. So what this again is saying is that we can actually find interval framers for continuous time and discrete time systems simply by construction. By constructing these embedding systems, we can do that. So we don't need to add any additional constraints to make this happen. So I want to also give a quick segue about interval observers, which we will talk about a bit more later on. But basically, whether it's a continuous time or discrete time systems with bounded noise, if we assume that all the uncertainties are bounded, including the noise and the initial condition, in this case, we assume that the nonlinear functions are differentiable and have known Jacobian bounds, meaning that we have Jacobian matrices, and each of the elements of the Jacobian matrix, we know the bounds of them. We know the upper and lower bounds of them. So using that, we can actually find an equivalent system that adds some additional degrees of freedom to the continuous time or discrete time system. And we can write down the embedding system that we talk about for this equivalent system. And that will actually give us our interval observer equations. And then we will have, we will find a linear comparison system and apply stability or gain minimization results from the literature to obtain observer gains to guarantee that, I guess, the observer that we get is ISSO, meaning that we have input to state stability. So in terms of minimizing some gains of system gains that we have, we consider both minimizing H infinity gains and L1 gains of the system. Specifically, one is H infinity and one is L1 gain. We showed that the H1 version will generally lead to a mixed integer non-convex problem, which is not great. But if we add some additional constraint to them, we can actually reduce them to either SDPs or mixed integer SDPs that will at least be solvable with all the tools that open off-the-shelf toolboxes that we can find out there. And specifically for this minimizing L1 gain, we can show also that we can reduce this to a mixed integer linear program. And it is already, I would say, with off-the-shelf solvers, there are a lot of them that can solve MILP exactly, so we are not losing anything here. But if we really want to, we can also add some additional constraints, and we get a linear program that we can solve. So this allows us to find the gains of the system. And just to give a plug on some of the work that we've recently done, is that we've also extended this to do state and input interval observers, and also to design hybrid interval observers, meaning interval observers for hybrid systems. Just to give you some simulation and what we are doing here, essentially, we just take a linear discrete time system. We see that the green line is the true signal of the system. We can find upper and lower bounds of them that frames all the states of the system. And using the different methods, I guess the red one is from some previous literature, whereas H infinity, well, sorry, the blue one is the one from a literature, and the red and the black ones are the ones that we can get using when we minimize the different gains. system gains that we have. So, and we can do this for continuous time systems as well. And again, the green line here is the true signal, and we try and find framers of them. And the blue ones are the ones from the literature. And the one that we've proposed is H infinity and L1. And those kind of converges. Essentially, the message is that the errors generally converges faster than what we have in the literature. Okay, so that was just the preliminary on mixed monotonicity and how that applies to interval observers. Now I will get into these robust control barrier functions that I wanted to talk about. And specifically for robust control barrier functions, we will be applying set membership parameter estimation. So the challenge with control barrier functions when they are parametric uncertainties has been considered for some very special classes of uncertainty. And some of them requires additional constraints, so some of them can be pretty conservative, I would say, meaning that sometimes you can find a controller that can keep the system safe, but the proposed methods cannot find them, or that they might not even guarantee it. So what is more important is that they generally don't apply when the parametric uncertainties are nonlinear or that they are time varying. And that's exactly what we are considering here. So we also have the challenge of reducing the conservatism of robust CBFs, and that's where we will bring in set membership parameter estimation. So basically, we want to make sure that we want to estimate the set of possible parameters that we don't know. And we want to make sure that the true parameter that can be time varying is within this set that we are computing. So there are certain methods that have been considered to do something similar, but again, they don't apply for time varying or nonlinear parametric uncertainties, which is what we are considering. So let's jump to what the problem statement is, or what's the system that we are considering. We are considering a pretty general control affine system with time varying nonlinear parametric uncertainty. We do assume that unknown parameters are time varying, but they are bounded, so we know the bounds of them. We also know that the parameters, because they're time varying, their time derivative will also be time varying, but they also stay within a set that we do know. So this here is just to define, I guess, the extension of what people consider as the candidate control barrier functions or the safety set. And now because we have uncertainty data, we are parametrizing with data. And the problem that we actually are solving, we want to make sure that because we don't know what data is, data star is something that can be time varying, but we don't really know it. We want to make sure that regardless of what they are, our CBF condition holds, meaning that we are robustly safe. So we are considering essentially the worst case data and data dot that can happen. We also want to make sure that we not only find robust CBF functions, but we want to find them such that they are computationally tractable and less conservative. So computational tractable in this case is that we want to write them such that we have conditions where they are going to be linear decision variables, such that if we include that into the safety filter that I talked about before, then it will remain a quadratic program that we can solve online. So we don't want to have any semi-infinite or for all constraints anymore. We want to make sure that everything is written in a way that when we plug it into the safety filter, it's computationally tractable, meaning we can use a QP for it. We also want to make it less conservative, and specifically, we do that by just being robust only to the estimated parameter sets, not the entire parameter set. So this here is just, again, a definition of what robust control barrier function is. Essentially, to skip the details, essentially it's just the previous CBF conditions, but now we enforce that it has to be satisfied for all possible values of data as well as data dot, because data dot appears when we take the time derivative. So again, if we stay within the set that we enforce for all possible values of data and data dot, then if we can do that, then we can guarantee that the system is going to be robustly safe. And then we can put that into the safety filter as part as the safety filter, and then we will be able to do that. So this is if we can find it, put it into this safety filter in a way that's tractable and computable, and that's what we are going to be talking about next. And specifically, at least we have different assumptions of that, but for the sake of this talk, I guess I will just focus mostly on parameter sets that are actually known intervals or hyperrectangles. And we assume that we know something about the functions being differentiable with known Jacobian bounds. So because of the assumptions that we make, the differentiability as well as known Jacobian bounds, we actually can show that there exist mixed monotone decomposition functions, which is why I talked about it before, for various different functions of the system. And if we have that mixed monotone decomposition functions for all of them, then we can actually turn that problem, the safety filter constraint that we have earlier, into one that's given by this here, where it's linear in U plus and U minus, which are the decision variables that we will have. And so this here remains linear in the constraints, and so this here is tractable. And again, this here is a sufficient condition. If we can satisfy this, then any Lipschitz continuous controller will actually render the system robustly safe. Just to give you a brief sense of what it is that we are using, we essentially use mixed monotonicity properties that I talked about, and we also use interval arithmetic for lower bounding the functions when we have not all sorts of nonlinear functions that are not in the form that would be very tractable to compute. So basically, we just lower bound them in a way that it will still is sufficient for robust safety, and we just essentially just apply mixed monotonicity property that I talked about, as well as in some places we use interval arithmetic because it's tighter. So we also propose alternative tractable CBFs method for under different assumptions. So if we have concave dependence, then we can use vertex enumeration. Or if we have linear dependence on the parametric uncertainty, we can use dual linear programming or robust optimization to deal with that. And one other thing we've shown is that, well, this here doesn't only apply to CBFs, it actually also apply to CLFs and control Lyapunov functions, where we can consider pretty general parametric uncertainty and use all sorts of methods for mixed monotonicity or vertex enumeration or robust optimization to get the system to be safe. So we can do both the control for the nominal part as well as the robust safety. So this is the next thing that I want to talk about is the second subproblem that we said. So first of all, I said I wanted it to be tractable, meaning that I want everything to appear linearly so that I can have a safety filter that we can implement pretty quickly on the fly using a QP, so that we don't have to wait too much to do it. So that's the tractable part of it. The second part of it is that we want it to be less conservative. So by wanting it to be less conservative means that we don't want to make it robust to all possible uncertainty, but we want to estimate what are the parametric uncertainties that are consistent with our observations that we have, measurements that we have, and we try to shrink these sets in a way that once we shrink it, then we have to be robust only to a smaller set of uncertainties. And that's the goal of, this is where we bring in set membership parameter estimation. So essentially, you can think about it as I start from all possible sets, all possible values of parametric uncertainties within a set. Because it's time varying, I guess we kind of expand it using, I guess, propagation, so that the states sets can be bigger just because it could vary with time. And then we try to intersect it with what we actually measure, what's consistent with our measurements. And that will then give us a smaller set that of possible possible uncertainty, parametric uncertainty values. So generally, this here will always get smaller and smaller. And generally it will be. So that's kind of what we are doing. So we want this set, we want to be robust to a smaller set, and that set gets smaller and smaller with time because we do set membership parameter estimation. So this first method that I'm talking here uses computational geometry tools. So the second method that might be more familiar to the people in the audience is to use interval observers, which I have just introduced earlier because I wanted to use it here. So basically, we leverage mixed monotone embedding systems, and we do that for this augmented system dynamics so that we can have the data appearing, the parameter appearing and becoming part of the state of the system. And using that, we can just write down the interval observer using this mixed monotone embedding systems that I talked about. And then we will then have this parameter set estimate at all times. So basically, we will estimate the set of all possible data, which in this case, for an interval observer, we guarantee that this set will actually be shrinking, or that it is the Framer errors or the errors, the difference between the upper and lower bounds will be input to state stable. Okay, so I guess, so that's what we essentially did. I guess we designed the interval observer. So I mentioned also that the interval observer can be designed to minimize certain system gains. In this specific case, I gave some of the equations for minimizing the L1 gain, which we can solve using a mixed integer program, which we can solve both for continuous time and discrete time. But I guess in general, we are using mainly the continuous time version of it. So we can, again, proof sketch is what we did before. We just use mixed monotone embedding systems, and with some equivalent system transformation that I also briefly alluded to, we can use some of the properties of the system to come up with this way of getting the gain, such that we can just use the interval observers with the gain that we compute from a MILP, which is simple to solve in general, and then we can just solve this. So just to compare with what is being done out there with CBFs, for some people in the audience might have heard that people have designed adaptive CBFs as well. And specifically in adaptive CBF literature, people would consider systems that are where the dynamics is linear in the uncertain parameter, and it's also assumed that the uncertain parameter is constant. So what's different in our case in terms of what we're doing is now we are actually considering the case that the data can be time varying, and we also remove the assumption that the dynamics can be nonlinear. So the adaptive CBF conditions have some equations that they can have. But what we found is that if your safety function itself is dependent on the data, they actually only guarantee that it's safe for the estimated parameter and not really for the true parameter, which is sometimes means that it's sometimes dangerous, or that it could happen where I guess it's not safe. And that's what we saw in our case. In our case, we proposed this robust CBF method. Specifically, I mentioned about using mixed monotonicity, but we have other methods to deal with them as well. And we can actually guarantee that it is robustly safe for all possible values of data that we estimated. And that's guaranteed to include the true parameters. So we are guaranteed to be robustly safe, whereas adaptive CBF is not guaranteed to be robustly safe. So this here is just to show a simulation example that we did for adaptive cruise control. It might be a bit hard to see, so we kind of zoom in a little bit and showed that if using the adaptive methods, which is the blue and the red one on the right figure, we can see that it actually dips under the safety conditions. So it's actually, well, actually all three of them, which is all the adaptive methods, yellow, blue, and red, they all actually dip under the safety boundaries. So they are actually not safe. So basically, we can find conditions for which they are not safe. Sometimes it can be safe if they are lucky, but it's not guaranteed. Whereas in our case, we can guarantee that the green line, which after you zoom in, you cannot really see it anymore, it's always going to be safe. So we also talked about using parametric or this parameter estimation type methods. Specifically, we tried the different methods, both methods that I talked about. And in this case, we actually saw that with parameter estimation, we actually allow the system to get closer to the boundaries, meaning that we are less conservative, as opposed to the fact that if we are just trying to be robustly safe to all possible variations of the uncertainty, parametric uncertainty, then we actually make it too conservative. We don't even allow it to get close to the boundaries, meaning that we are probably giving up something. Of course, this comes at a cost when we do parameter estimation. Whichever method that we use, actually it incurs additional time. In general, I would say that using the interval observer, which is the second method that I talked about, just has a small overhead of time compared to not having parameter estimation at all. And that small overhead of time allows us to get the results that I've just shown here. We can get closer to the boundaries. So the next thing that I want to talk about, which is the next part of the talk, which I will probably have to go a bit quicker through this, is to talk about the case where we actually don't know what the system is at all, but we have some data. There are methods that have been proposed using neural networks or Gaussian processes, but in general, they either don't have guarantees or that they only have probabilistic guarantees. With the exception of a specific paper that I'm showing here, but it assumes some continuity assumptions that can be pretty strong. And it also ends up having second-order cone programs that are computationally really expensive to implement. So what we've shown, we're doing here is we are assuming that the system is not known at all. The H function is known. We assume that it's known. The safety criteria that we have is known. We don't know what the true dynamics is of the system, but we assume that they're continuous. We assume that H dot, because we don't know what F is, H dot is not known. But we assume that there is trajectory data that we can use. So we are going to be assuming that this H dot function has some continuity properties. So either it's globally Lipschitz or globally component-wise Lipschitz or differentiable with globally bounded Jacobians. And by making these assumptions, we can actually make sure that even though if we don't know the system, but we have some data, we can still make the system robustly safe. So this, what we are doing here, which is tying back to the interval methods or seminar, is that we do set membership learning. So there's this method that has a lot of names called set membership prediction, Lipschitz interpolation, kinky inference. Essentially, this is just a non-parametric learning approach that bounds the unknown function from the top and bottom. So it's an interval bound. And specifically, depending on what the continuity assumptions we have different functions that might be easy or harder to use. And specifically, I guess, we generally want the bounding functions to be affine or piecewise affine so that we can actually solve them. We don't want it to be non-convex because then everything will be intractable when we actually try to apply it. So the idea here is we want to leverage set membership learning, and specifically, we want to lower bound what H dot is using data. And this can actually be done directly from continuity definitions or again using mixed monotone decomposition functions for bounding. And that is given here for the different types of assumption that we make. We can have different ways of lower bounding them. And this essentially allows us to bound what the true function. So we want to bound the true function from below because that will allow us to make the system robustly safe. And specifically, the one that is closest or the tightest, I would say, compared to all the other assumptions is that if we have this globally bounded Jacobians, which is a stronger assumption than Lipschitz continuity, then we actually have a bound that's closer. So this here is just quickly to show that they are, for each of the different continuity assumptions, we can write down robust CBF conditions, and all of them are tractable in the sense that all the variables that show up would be just kind of linear or will result in some mixed integer type, linear type of constraints that off-the-shelf solvers can just solve. So the main issue that we have when we have piecewise affine functions, which is what we will end up getting for the assumptions that we make, we actually have mixed integer quadratic programs, which they are off-the-shelf solvers to solve, but they are not as fast as quadratic programs. So we actually propose some complexity reduction strategies as well. And first of all, I guess we assume we kind of decompose the mixed integer quadratic programs into multiple quadratic programs that you can solve in parallel, or that some of the times or many of the times they actually have analytical closed form solutions as well, so they can be easily implemented. And we just have to solve a sub problem, and they will just be a QP. We just have to solve all of them in parallel, and then we just consider all the possible solutions that they are, and just pick the one that's the smallest, and that will actually solve that problem. So another complexity reduction strategies is to really deal with the fact that the set membership learning methods really becomes even more complex when we have more data. So instead of considering all the data all the time, we just consider what we call a subset of the nearby data by again leveraging monotonicity of the learning approach. So we can show that the learning approach is monotone to some extent in terms of the number of data points. So if we just consider nearby data, we can show that this here is going to be robustly safe as well. So I guess this here, again, sometimes when I talked about this Lipschitz continuity assumption or Jacobian bounds assumptions, we sometimes don't have the Lipschitz constants or the Jacobian bounds. We propose some way of also computing what these Lipschitz constants are and what these Jacobian bounds are. And they can be estimated with high probability, meaning that the more data you have, then the closer you get, or there is, if there is a certain number of data that you have to get within a certain probability to the, with very high probability, you get to the actual true Lipschitz constant and Jacobian bounds using packed learning, probably, I guess, approximate learn. I cannot remember what the C stands for. Approximately correct learning, I believe. So this is just to quickly jump to the example as well, to say that we applied that to a problem that was considered in a paper that was done here. Specifically, this paper, as we have here, ends up with an SOCP, which is the second order conic program that usually takes a long time to solve. We tried that, and on our machine, it took I guess 2.84 to 10 to the power of 5 seconds to solve all this, whereas all our methods can do it much faster. And we can show that when you apply also to adaptive cruise control problem, that our system would be safe, even if we don't know the model, but we have data, so we still make sure the system is safe. So just to summarize, we talked about robust control barrier functions for uncertain systems. Specifically, we consider uncertain parameter varying systems, so time varying systems. We use mixed monotonicity. We use concave bounding or robust optimization. We also have set membership parameter estimation to shrink the set of uncertainties that we need to be robust to, and we can again use mixed monotonicity based interval observers or using some computational geometry tools to do that. We also talked about unknown continuous time systems with only prior trajectory data, where we then use set membership learning under various continuity assumptions. We also propose, I guess, complexity reduction techniques so that this here can be actually used and actually be fast enough. So some other challenges or opportunities that we might have is, I guess, if we can have more computationally efficient or tight set membership parameter estimation, then we can be less conservative. So we could potentially consider zonotopes or polytopes when we're designing the observer. So maybe if we do that, that would help. And sometimes we might want to consider how do we deal with the nonlinearity of the systems? Can we consider linearizations of the system or immersions of the system? And we also want to be able to more reliably estimate the continuity parameters, because actually this especially for the set membership learning method that I talked about, when the functions are not known, how tightly we can estimate these constants actually affects the performance of the system. So we do want to find ways to estimate them more reliably. And ideally, we want to have confidence or error bounds for these constants or bounds as well. So there are probably much more opportunities for learning control barrier functions. Specifically, we assume that the safety function is given, and we're just trying to robustly make sure that the system is safe. But I guess maybe we can learn what should the safety function be from demonstrations. And we could potentially use set membership learning methods as well for that. And I guess one important thing is when we are trying to learn the safety boundaries, how can we be safe while we actually do that? One final thing is something that we have been doing in my group is that what if maybe we can actually directly, if we are given the system to some extent, can we actually derive the function itself and incorporate what we call future information to make sure that it's less conservative. So future information here is just basically saying that if I'm driving on the road, I actually can, because I have camera systems, I can see ahead of time a certain distance ahead of me, so I know what the road disturbances would be. So how can I take this future information into consideration when as a preview of the information, so that we can take that into consideration when we make sure that our system is safe, and so we don't have to be robust to the uncertainties in the future, but we can take that into consideration and be less conservative. So with that, I just want to thank you for your attention. I know I went a bit fast through some of the parts. And before I take questions, I just want to acknowledge, I guess, the sponsors of this project, NSF, DARPA, my previous institution, Arizona State University, and my current institution, Northeastern, as well as my current and former students that have worked on this project with me. One of them, I guess you just heard from, and the middle one was presenting something related to what I was talking about in a previous talk on this seminar series as well. So look up the website and look at the talk if you would be interested. So at this point, I'll be happy to take any questions that you might have.
So many thanks, Yong, for your very interesting presentation. And yes, as you just suggested, the floor is now open for discussions. Who wants to start? Okay, let me check. There's no one who has unmuted him or herself at the moment. Tarek, you want to start?
I can start. So many thanks for this very interesting presentation. I have two short questions.
Yes.
The first one about slide 14. it was not clear for me how the H infinity criterion is determined in the nonlinear case. It was not clearly.
Oh, you mean for the interval observer in the earlier part of the talk?
Exactly.
So yeah, I guess you're right. I guess
Possibly.
the gains that we actually are defining when we say we are minimizing the H infinity gain or something, we're actually defining it for the comparisons, linear comparison system. So
Okay.
it's not the true H infinity gain, it's just for the linear comparison system. So basically we find the comparison system first and then we do the H infinity gain.
It's a suboptimal solution. Yeah.
This
Yes.
is a suboptimal solution. You are right. I guess it's not the true nonlinear system that we are doing it for.
Okay, and the second one, it's a small question also for slide 30. Are there some assumptions, for example, the persistency of excitation, the observability, to estimate both of the parameter vector and also the state? Yes, for the
that's a good question. I guess if we do adaptive CDF, I guess they actually don't assume. There are adaptive CDF papers that do assume this persistence of excitation. But in this specific work that I'm trying to review here, they actually don't make the assumptions. So they actually are using more of the indirect methods for adaptive control, where it doesn't really need it. They just it doesn't. That's why it doesn't necessarily converge to the true parameters. But which is why I guess it's sometimes not guaranteed to be safe. Well, in some conditions it does, but it's not always true. That's why it's not robustly safe. It's robust. It's safe for the estimated parameters, and there is no guarantee of that the data head will actually converge to data unless you assume persistence of excitation. For the robust version that we propose, if we consider the big set of data and data D, then if we robust against the worst case, then there is no need for persistence of excitation. But if we actually are doing this parameter estimation, then I guess they could be, I guess we only have sufficient conditions. If the system has a certain property, it actually doesn't really need persistence of excitation. So I guess it's just like if we are doing interval observers, we are not finding a specific signal. We are finding only upper and lower bounds of them. So when we design interval observers, which I know that you do too, we actually don't need any persistence of excitation there. We just need properties of the system that will allow, I guess, the framer errors to kind of converge instead.
But you need the observability, I think.
Yes, you need observability in that case.
Okay. Yeah, okay, thank you very much. Thank you.
Okay, do we have further questions? Yes, Nasim.
Okay, thank you. Thank you for a very nice talk and very inspiring research directions. I would like to comment about the set membership learning. Usually in the literature and your work as well, you rely on assumption of Lipschitz that the hidden system has Lipschitz conditions. And I would like to know your opinion. I mean, I believe this is quite a strong assumption. So how far or how is there any way we can lift this kind of assumption?
That's a good question. I guess when we don't have the model itself, there's not that much that we can do. Or I mean, it's not that there's not much we can do. It's not much that we can guarantee unless there is some assumption. So I guess one way of learning is, I guess, people do parametric methods. Either you assume the form of the function is known, or in our case, we assume some continuity assumptions. So I guess Lipschitz continuity, you're right, it's actually pretty strong assumption, which is why I guess people tend to go with what this component-wise, I guess, did I mention component-wise Lipschitz constant? So basically, for each dimension, the Lipschitz constant is different. Then that is slightly less conservative. But I would say that unfortunately, we would need some continuity assumptions. Otherwise, the function can be anything when it's not known. So we need some form of assumption. So either it's continuity or parametric form. Or if you have any thoughts about like what are the reasonable assumptions we can have, then I guess I would be glad to explore them also. I guess my message here, I want to say here is that I guess I think that it's impossible to do it without any assumptions.
Yeah, of course, I do agree. But if you are, I guess the idea is to study safety for systems that may embed some machine learning components, this kind of application domains. Is there any chance we can extract some properties knowing that the system is indeed embedding a machine learning component?
I guess I mean, if it depends on what you mean here with the machine learning component. If the controller itself is using some machine learning methods, I guess it's fine because we are only doing the safety filter. The nominal controller can be based on any machine learning technique also. Doesn't have to be this closed form controls.
But the sensors, reception sensors.
Yeah. So
yeah.
So I guess that's also that's definitely something that people are studying. Is that I guess when you do machine learning techniques, can you actually also find what they call generalization bounds? Basically, what set membership learning is doing is trying to find generalization bounds. My take of what I would do is I would take the data that people use to learn the machine learning component and use this set membership learning approach on the same data to get the generalization bounds if we have access to the data. But if we don't have access to the data, we only have the models only, then I guess it's hard to know what the generalization bounds are unless we assume something else.
Or at least you are suggesting that those people doing indeed the machine learning approach, they could also at the same time embed the set membership learning component that would provide them. Yeah,
that would be great.
Very nice. Yeah. Okay. So very nice idea.
Yeah, use the same data to do both. Get the generalization error and get the machine learning model.
Yeah, that's a research line.
That's
the conclusion of this. Thank you very much. Thank you very much.
Do we have further questions? Okay, at the moment I do not see any further questions, but let me ask one or two questions. Firstly, what I like very much at the end is also how you indicated that your approaches outperform corresponding alternative approaches concerning the computational effort. And do you have some information concerning the scalability of your approach? How well does it scale with growing dimensions of the state vector?
I guess, are you talking specifically about the learning case?
Yes, especially concerning the learning case at the very end.
Yeah, so I guess I mean, I think the bigger problem here, one problem is definitely state dimensions. The other problem is actually just the fact that it's a non-parametric learning approach. The non-parametric learning approach actually doesn't scale well with the number of data points. So I guess the thing that's why we actually propose this, I guess, complexity reduction strategies, specifically using downsampling or to solve it using parallel computing. That will kind of actually, especially a downsampling method, will kind of overcome the problem with scalability with respect to number of data points. But then I guess that's the other question of, I guess, state dimensions, right? I think we do have certain techniques that we developed that we kind of give up even more optimality to get piecewise affine, I guess, hyperplanes that are at least easier to deal with. So I think a lot of these methods, I guess, all these methods really is we have to, if we want to make it faster, then we have to give up something. And usually is conservatism that we are paying for it. And that includes our methods as well. So I guess I think that the state dimensions is not as big a problem as the number of data points. At least that's so far what we've done. But that's why we did this downsampling method. But yeah, we haven't really exactly explored what is the limit in terms of how many states we can deal with. But theoretically, there is no limit to it. But then the computationally, how easy it is to compute it is a question that we have. But I would say that it's not that big an issue, because if we end up having QPs as, I guess, the sub-problems that we're solving, we know that QPs, people have solved them for like almost 1 million or millions of state decision variables. So I would say that probably states is not that big an issue, or as big an issue.
Okay, great. And with this answer, you have already stolen my second question, the follow-up question concerning the complexity reduction.
Okay.
Yeah. Okay, now let's have a look at the audience. Is there still anyone who wants to ask something? This doesn't seem to be the case. Then again, thank you very much for your very interesting presentation. And really, we appreciate it very much that you have been the first speaker after the restart of our seminar. Yes, and to the rest of the audience, we're looking forward to our next presentation, which we will have on Friday in 2 weeks. And here's the next speaker will be Daniel Silvestre from Lisbon, in Portugal, who will give the next presentation in our seminar series on Friday, the 27th of October. And yes, from that point of view, have a nice remaining Wednesday, either afternoon or evening. And yes, see you very soon in one of the follow-up presentations in the seminar series.
All right. Thank you again, everyone. It was nice meeting you all.